directional derivatives and gradients. Suppose that you want to find the directional derivative of the function at P in the direction of V. You are given a function 3x minus 4xy plus 5y. You are given a point and you are giving a vector that gives the direction that you want. I plus the square root of 3j. Now, the first thing you want to do is you want to get v to be a unit vector. You want its length to be 1. Now, possibly it is. Remember, if you have a number in front, you just take the absolute value of it. And then it's 1 squared plus the square root of 3 squared. The absolute value of a half is a half. 1 squared is 1. The square root of 3 squared is 3. You have half times the square root of 4. Half times 2. It's 1, which is good. If it weren't 1, we would divide it by this number. We would divide v by that number. If it was 7, we divide by 7. Now, the formula for, so now we actually call this unit vector u. Make this vector, scale it down to a unit vector. It happens to be a unit vector. That's the vector u. The directional derivative in direction of v of f of xy is just the gradient times gradient of f dotted with the u. Now, the gradient of f is just the partials. It's the partial with respect to x. That's 3 minus. This is like 4y times x. 4y is a constant. The derivative of a constant times x is just a constant. Plus 5y is a constant. Its derivative is 0. It's fx comma fy. The derivative of 3x is 0. Minus 4x is a constant. The derivative of y is 1. So you just get 4x. Plus the derivative of 5y is 5. And u is, you don't even really need to half it. It's 1/2 1 square root of 3. 1i plus square root of 3j. We dot this. We dot it. We dot the 2. We dot these 2. So dv of fy is we dot them. Well, the half comes along for the ride. We multiply this by 1, and of course we get that, plus we multiply this by the square root of 3. The square root of 3 times negative 4x plus 5. And that would be the directional derivative of the function of x and y. But they gave us a point. Remember, they gave us the point 1, 2. Now you could have plugged that information in earlier. You can plug it in now. I'm going to plug it in right now. So the directional derivative of f in the direction of v at the point 1, 2. At the point 1, 2, well, it's 1/2 times 3 minus y is 2. 4 times 2 is 8, plus the square root of 3 times negative 4 times x. Since x is 1, it's negative 4 plus 5. In fact, that's just 1. So I have the half in front. 3 minus 8 is negative 5, plus the square root of 3 times 1 is just the square root of 3. And there it is. That's your directional derivative. Find the gradient, get the vector v to be a unit vector, and then dot the two. Dot the unit vector in the direction of v with the gradient at the indicated point. For example, if they tell you that g of xy is the square root of x squared plus y squared, and they give you the point being, say, 3, 4, and they give you the vector v is 3, negative 4. Well, you should know the length of that vector. I mean, we just see it all the time. It's 3 squared plus 4 squared square root. You need to start learning your Pythagorean triples. 3, 4, 5. It's 5. 9 plus 16 is 25, and the square root of 25 is 5. So the vector u will be the vector v, where we divide by 5. That's now a unit vector. If you square the I component, you get 9 over 25. If you square the j component, you get 16 over 25. And you take the square root. That will be the length of u. But that's 25 over 25. The square root of that. The square root of 1, which is 1. The length of u is 1. Find the length of v and divide v by that length. Whatever it is, divided by that. And you will then have a unit vector. Okay, so we have the unit vector, which is good. Now we have to find the gradient. The gradient of g. Well, remember, g is x squared plus y squared to the half. So we take the derivative with respect to x first. You bring down the power. You make the new power 1 less, which will be negative a half. If I put it in the bottom, it'll become plus a half. So I brought the power down. I made the new power 1 less. Now I have to multiply this by the derivative of what's inside there with respect to x first. And that's 2x. 1 times 2x is 2x. Naturally, the 2's cancel. Now I do the same with respect to y. But this function is very symmetrical in terms of x and y. If you interchange x and y, you get the same function. That is, if I put y instead of x, and I put x instead of y, I get back the same function. The partial is going to live up to that as well. X becomes y. Y squared plus x squared, which is the same as x squared plus y squared. That's the second partial. The gradient, by definition, is g sub xi plus g sub yj, which in another notation would just be this. So it's the partial with respect to x, comma the partial with respect to y. Okay, so we have the gradient, we have the unit vector. Now we dot it and we call that our, well, now I can plug in the values. The gradient of g at the point 3, 4 equals, well, x is 3, and the bottom, 3 squared plus 4 squared, that's 5 squared. The square root of that is 5, comma, y is 4, the bottom is still 5. 3 squared plus 4 squared is 5 squared. But we don't just want 3 squared plus 4 squared. We want the square root of that. Okay, and we have good old u. We dot the two. The directional derivative in the direction of v at the point 3, 4. Well, I multiply this number with that number. And I get 9 over 25. Plus, I multiply this number by that number, which actually is minus 16 over 25, which is negative 7 over 25. And that's the directional derivative in the direction of v at that point. That's like the slope. Now, this time they want to find the directional derivative of the function in the direction of u is equal to cosine theta sine theta. Now, this happens to always be a unit vector, because when you square the I component plus and you square the j component, you get 1. And you take the square root, you get 1. The length of this u is 1. Okay, which is good. So you should know that so you don't spend any time figuring it out. Cosine squared plus sine squared is 1. Oh yeah, I take the square root of 1, but it's still 1. And they tell us that f of xy is x squared plus y squared, and that the angle they would like us to use is pi over 4. They're not really giving us a point. Alright, so we need to find the gradient. The gradient of f of xy. The partial of that with respect to x is 2x. The partial of that with respect to x is 0. It's a constant. Comma. Well, they're symmetrical again. If this is 2x, that's going to be 2y. We can work it out. The partial of x squared with respect to y. Well, x squared is a constant. So the derivative is 0. Plus the derivative of y squared with respect to y is 2y. Okay, and we have u. It's cosine actually pi over 4 comma sine pi over 4, which means it's the square root of 2 over 2 comma square root of 2 over 2. That's u. So the directional derivative in the direction of v of f of xy is the dot product. It's this times that. The square root of 2 over 2 times 2x. The 2's cancel, plus product of those two numbers, or expressions. Again, the 2's cancel. So you get square root of 2x plus square root of 2y. If you factored out the square root of 2, you get the square root of 2 times x plus y. xy is x squared plus 4y squared. You want to find the directional derivative of the given function at the point P in the direction of Q. So here's a direction, and here's which we're calling Q, and there's the point P. And P is the point 3, 1. The Q is the vector 1, negative 1. Actually, what I said is not true. I don't know what I was thinking. Q is a point. Q is a point. You have P being 3, 1. Put it right here. And here's Q. This is Q, which is 1, negative 1. So that's the direction they're talking about. Q is not a vector, I'm sorry. Q is a point. But you want to go from P to Q. You have the point P, but the point Q gives you a direction. You walk out of your house, you're somewhere. You're at the point 3, 1. Where do you go? Well, you have to have some plan. The plan is you're going to visit Q. So what is this vector? Well, we have the tail and we have the head. 1 minus 3, negative 2. Negative 1 minus 1, negative 2. So now you have a vector. Okay? You want the directional derivative in this direction. So this information, we're updating it with v is equal to this. V is equal to that. But we have to scale it. We have to make sure it's a unit vector. Now, if I just divided by 2 or negative 2, I would get 1, 1. That's in the same direction. It's in the same direction. Just worrying about that negative sign. Let's see what's bothering me. Negative 2 is right there. And that's the direction. 1, 1 is right there. So it did change directions. Alright, so maybe we shouldn't play games with that. You shouldn't divide by a negative number. But I'd rather the numbers be smaller, because smaller numbers, I have less of a hard time figuring out the length. But nonetheless, their length is this squared plus this squared square root. It is the square root of 4 times 2. I know the square root of 4. I do not know the square root of 2. Since I'm dividing, I'd rather multiply this by square root of 2 over 2. Over square root of 2. Multiplying by 1. The top will be 4. Square root of 2 times square root of 2 is 2. Times another 2 is 4. Divide by square root of 2. You'll see why I did that. Because I want u to equal v divided by the length of v. I want it to be negative 2 divided by 4 over the square root of 2. There are no radicals in the bottom now. And I can factor out, say, a 2. So I get 2 square root of 2's times negative 1, divide by 4, that becomes 2. So it's the square root of 2 over 2 times negative 1. I can factor out the negative sign. Okay, so I have my unit vector in the direction of P to Q. Point P, go in the direction of Q. So you're going from P to Q. And this vector would do that. Actually, I want to be very clear. It doesn't do that. I'm not going to plot these right, but if this was P and this was Q, that's the vector, but we're really using this vector. Same length, but it starts at the origin. Vectors can be moved up, down, left, and right. You can't rotate them, you can't make them longer, and if you did, it's no longer the same vector. It might be twice the vector, but it's no longer the same vector. Okay, so now the directional derivative of f of xy in the direction of v is, first we have to find out the gradient. So the gradient of f is the partial of this with respect to x is 2x plus the partial of that is 0. Okay, now we do partials of y. Partial of x squared with respect to y is 0 plus the partial of this is 8y. And if you want, you can factor out the 2. Now you just dot these two vectors, this vector and this vector. dv of f of xy is, well, first you multiply the constants. That's just going to give you the square root of 2, because these 2's cancel. Then you multiply x by -1, and then you multiply 4y by -1, and there's your answer. This, or you can factor out the negative. Either one of those, 100% correct. Now, of course, something happened here. Of course, we're supposed to add. We're not supposed to get a vector. So, I multiply the constants, and then x times -1 is -x plus 4y times -1 is -4y. So -x plus -4y is -x minus 4y. And you can factor out the square root sign, and the negative sign, and you get x plus 4y. And then the last thing I will do is I will plug in my point P, 3, 1. X is 3, y is 1. 4 times 1 is 4, 3 is 3, 3 plus 4 is 7. So it's -7 square root of 2. That's the directional derivative at the point 3, 1. Q, the point Q that they talked about just gave us the direction. There was a point P in the direction of Q. But nonetheless, the point was still 3, 1. -7 square root of 2. So be careful about ignoring negative signs because they change the direction. Okay, so we're going to do another problem exactly the same type. You're given a function, and it's defined to be ln of, how about x plus y plus z? You have a point 1, 0, 0. And you want the derivative from at that point, but in the direction of Q, where Q is 431. I made a mistake crossing out P earlier. We're not going to need Q, but for now we still need P. So you're going from P to Q. So you do head minus tail. And we call that vector V. 4 minus 1 is 3. 3 minus 0 is 3. 1 minus 0 is 3. That's the vector V. The length of V, well, you square 3, and you square 3, and you square 1. 9 plus 9 is 18, plus 1 is the square root of 19. If I multiply the top by square root of 19, I'll get 19, and I have to do the same to the bottom. I'd rather have the radical in the bottom, believe it or not. Vector U is vector V, 3, 3, 1, divided by the magnitude of V, which is 19 over the square root of 19. That's U. Its length is 1. Calculate the length, so you'll figure out that it's 1. Okay. So now I need to find the gradient of H. Now remember, the derivative of ln of anything, you put the anything in the bottom and the derivative on top. First is the partial with respect to x. The derivative of x is 1, but the other letters are constants. X plus a constant plus a constant, the derivative is 1. Okay, now we take the derivative with respect to y. The derivative ln of anything, you put the anything in the bottom, and the derivative with respect to y on top. X and z are constants. The derivative of what I circled is 0, plus the derivative of y is 1. And you're going to get the same exact answer for z. There's a partial of z. That's h, that's delta h. Now, if I plug in the point, x is 0, excuse me, x is 1, y is 1, and x is 0, y is 0, and z is 0. X is 1, y is 0, z is 0. 1 plus 0 plus 0 is 1. In fact, all the denominators are 1. In fact, 1 is on top. 1 divided by 1 is 1. Okay, this is just the vector 1, 1, 1. This is just the vector 1, 1, 1. Plus x plus y plus z in the bottoms are 1, and the numerator is 1. You get 1s. Okay. And we have u. We dot them. Directional derivative of f of 1, 0, 0. And the direction of v is, you dot them. The constant tags along. Square root of 19 over 19. 1 times 3, not a vector. 1 times 3 is 3, plus 1 times 3 is 3, plus 1 times 1 is 1. This is 7. Square root of 19 times 7 is the same as 7 times the square root of 19. And do not forget to divide by that 19. And there is your directional derivative. Work these out. They're definitely doable. If they weren't doable, I wouldn't be able to do them. The next problem says, find the gradient of the function and the maximum value of the directional derivative at the indicated point. Okay. give you a function, f of xy is equal to x squared minus 3xy plus y squared, and the point is 4, 2. Now, it turns out that the magnitude of the gradient is going to be our answer. The magnitude of the gradient is the maximum value of the directional derivative. Right. So, actually, just the magnitude of the gradient. So, the gradient of f of xy is, first, partial of x. 2x minus, this is 3y times x. 3y is a constant. The derivative of a constant times x is the constant. Plus y squared, the derivative of that with respect to x is 0. Okay, now I do it with respect to y. X squared, that's the constant. The derivative is 0. Minus 3x times y. The derivative of a constant times y is just the constant. Plus the derivative of y squared is 2y. That's the gradient of f of xy. So what's the gradient of f of our indicated point? 4, 2. 2 times x is 8, minus 3y is 6, so that's 2. And negative 3 times x, x is 4, that's negative 12 plus 2 times 2, which is 4. Negative 12 plus 4 is negative 8. So that is my gradient. What we want is the magnitude of the gradient. It's 2 squared plus 8 squared square root. It's 4 plus 64 square root. The square root is 68. But the square root of 68 happens to be, 68 happens to be 4 times 17. And the reason I pick 4 times 17 is because I know the square root of 4. And it's the largest number that goes into 68 I know the square root of. I have no idea what the square root of 17 is, nor can I break it down. So there is the answer. 2 times the square root of 17. That is the maximum value of the directional derivative at the indicated point. You need to walk around knowing that. What's the maximum value of the directional derivative? It's the magnitude of the gradient, of course. That way when you see that on an exam, you don't panic. You go, oh, that's just the gradient. I know how to find the gradient. Okay, same problem. Suppose you're told that g of xy is equal to ln of the cube root of x squared plus y squared. And we're concerned about the point 1, 2. Now, in terms of finding the gradient, whenever you have ln, you want to simplify it. You want taking the derivative to be easy. Cube root means to the third. Now, you can take what I'm taking ln of and put it in bottom, and then go on and try to figure out what the derivative of that is and put it on the top. Or you can say, you know what, this power is bothering me. Let me just bring it in front. It's 1/3 times the ln of x squared plus y squared. When you have ln's, you shouldn't have products. because if you had the ln of one thing times another, at the ln of that, well, it's just the ln of the first plus ln of the second. Ln of A times B. It's ln of A plus ln of B. No more product. So you wouldn't have to use the product rule. In fact, if you have a very messy problem, you might want to take ln of both sides, and then you could break down the messy part. Okay. So we want to find the gradient of G. That is, I want to first take the partial of this with respect to x. Well, the third comes along to the right. The third times the derivative of this. The derivative of ln of anything, you put the anything in the bottom, and its derivative on top. First, we're taking the derivative with respect to x. And then again, if you look at the original problem, if you interchange x and y, you get back the same answer. What you're going to get is 2y over 3 times y squared plus x squared. Or you can say, there's this 3, the derivative of ln of anything, put the anything on the bottom, and put the derivative with respect to y this time on top, which is 2y. So that's the gradient. But I don't want just the gradient, I want the gradient at this point. X is 1, 2 times 1 is 2. The bottom is 3 times 1 squared is 1 plus 2 squared is 4. 1 plus 4 is 5, comma, y is 2. 2 times 2 is no longer 2. It is 4. And the bottom's not changing, it's still 15. Okay, so now I can find the maximum of the directional derivative. It's just the length of this. Remember, this is 2 over 15. So it's 2 squared over 15 squared plus 4 squared over 15 squared, which is 20 over 225. The square root of 20, which I'll think of that way, divided by the square root of 225. The square root of 225 is 15. After all, how did we get 225? And the square root of 4 is 2, and the square root of 5, I don't know. Here's your answer. That's the maximum gradient possible at that point. At that point. Different point, you'd get a different maximum gradient. Excuse me, maximum directional derivative. Okay, let's see what we can do next. How about we try this one? Use the gradient to find a unit normal vector to the graph of the equation at the indicated point. So they give us this equation, and they give us the point 210. They want us to use the gradient to find the unit normal vector. You want to find the unit normal vector. Well, the gradient is simply, so what you should first do is define f of x. Set your equation equal to 0. It is bring the 6 over. F of x is 4x squared minus y minus 6 is 0. Okay, so the partial with respect to x will be 8x. The partial with respect to y will just be negative 1. And then the gradient at the point 2, 10 will be 8 times 2 is 16. And when x is 2 and y is 10, negative 1 is negative 1. Now, the length of the gradient of f of 210 is 16 squared plus 1 squared. 16 squared is 256 plus 1 is 257. Want you to see the 16. So what you have is the vector 16, negative 1, and you want to make it length 1. That is, you want to divide by the length. This is the same as our 257 over the square root of 257. The square root of a number is 1 over, is the number over the square root of a. The square root of a is a over the square root of a. I know it is, because square root of a times square root of a is a. So I divide by the length. 257 divided by the square root of 257. And that gives you a unit vector, a unit normal vector to the graph at that given point. That finishes up this section. Thank you.